carbon bonds are there in one molecule of cis 1,2-dimethylcyclohexane? So when it came to this question, the best thing to do before you answer it was just to draw out the molecule. You have it in the name. So cyclohexane, we know we're dealing with a hexagon. And then it says cis 1,2-dimethyl. We have two methyls. Any two carbons you would have chose would be fine. And then they're facing in the same direction. So let's like put them both on wedges. There. This is cis 1,2-dimethylcyclohexane. So now, how many carbon-carbon bonds do we have between all of these carbons?
1, 2, 3, 4, 5, 6, 7, 8.
Right, 8.
Like I just answered too. Okay.
8 carbon-carbon bonds. Yeah, there were some pretty good, simple questions on this exam. I liked it. It was very fair. All right, let's move on to question 6. It says the electrons in pi bonds are usually higher in energy than non-bonding electrons. Is this true? So, to answer this question, we have to remember the little energy scale we have for certain type of bonds, right?
Yeah, I draw that thing to help me out. So I put
Right.
bond, sigma bond on the bottom.
Right, that's the lowest always.
Then
so sigma
pi,
bonds. Exactly. Then pi bonds.
then
Above pi bonds is
non-sigma bond.
right, non-bonding electrons. And if you want to go further, that's when the anti-bonds come in. So then I believe it's pi anti above non-bonding, and then non-bonding anti.
Save olds.
But
Well, we don't have
we
any.
already know these coexist, so that's why we don't normally pay attention to those. We pay attention to these mostly. So it says here that pi bonds are usually higher in energy. Is that true?
No.
No. The answer for this would be false. Non-bonding electrons are higher in energy than pi, always. So you always have to remember this little chart. It'll help you through a lot of questions. Yeah. Now let's do question 7. What is the correct order of basicity for the elements listed? So according to the answer choices, we're going from most basic all the way to least basic.
Okay, so
yeah, we're going from most to least, and we're dealing with.
We're going to Candlelight.
Let me just write the. We're dealing with carbon.
Candlelight's on Central Avenue by the 4-H bar. It's a restaurant.
And oxygen.
I know his friend.
So for help me with this question, I put that basicity is going from.
You were not.
Right to left.
I was. I had more damage than Robin. 2 killed 4 players.
Exactly. On the periodic table, basicity increases right to left on the chart. Exactly.
Was in all of our
so, you have.
He really was being a bitch.
Yeah, me too.
Which one do you know is definitely?
I say Dick because my name is Richard, and that's why.
Carbon.
Exactly. So carbon goes first. After carbon is what?
Nitrogen.
Right.
All right. Is Aaron nearby?
Right. And then lastly, fluorine. So this was the order of basicity from most to least. Right. So basicity increases the same way electronegativity.
This is probably one of the most fun games ever to play with your friends, chat. I know most of you probably don't have any friends, but check our community
That's one good
Discords.
periodic trend to remember to help you with basicity and acidity. Alright, question. Let me do a different color. Question 8. 3 functional groups found on this compound are what? So let me draw out the compound. You had a cyclohexene, and you had OH. This was COCH3, and then OCH3. So,
okay,
It's about learning your functional groups. So can you identify these 3 functional groups?
Maybe.
Let's see. What's the easiest one we can identify here?
Alcohol.
Definitely. Alcohol just screams OH. All right. What other functional groups do we see?
I see a ketone on next to the
Yes,
Yeah.
exactly. This is a ketone. And then what's that last one on the bottom?
and ether.
Right. It is exactly ether.
Oh my.
So the answer choice that matched this was like if you have version A.
Mhm.
Is this version A or B? I'm trying to remember. Oh, this is version B. So version B, well, all the answer choices is supposed to be alcohol, ether, and ketone. The
Wait.
answer choice for that in either version. I think for B it was B. At A, I don't know. It could have been C, D, A.
I think it was A. Wait, Mr. Kimmy, what's an aldehyde then?
An aldehyde? Oh, so an aldehyde is R. You have your carbonyl group, and then the other attachment is just a straight up hydrogen. This is your aldehyde.
Dang. Okay.
Yeah.
Isn't the cycle will be an aromatic or something like that?
Oh, so no. The cyclic ring, it only has one double bond. In order for it to be aromatic, it would have been if it was like this. This is known as an aromatic ring.
Okay.
But because that just has one, it's not aromatic.
I was confused, but I choose my alcohol, ketone, and ether. I was like,
Yeah, good. Yeah, because aromatic is definitely not one of the choices here. All right, cool. So now let's do the other question. Question 9. What kind of reaction is shown below? So let's draw it out. You had a cyclohexene with a methyl, and then it undergoes some type of reaction with Br2 in water to get well, this was a cis, and then OH was on a wedge, and bromine was on OH was on a dash, bromine was on a wedge. All right, so this happened. The reactant was this, and then the product ended up being this. What type of reaction do you think they placed at? The choices was elimination, substitution, addition, and it was Bronsted acid base.
addition.
Exactly. Addition was definitely correct. It wasn't elimination because we're not eliminating. So elimination is actually the opposite of an addition reaction. So for example, this was addition, right? Going this way is addition. For elimination, it would have been if you went the other way. So from here, from the reactants to this product here is an elimination reaction. Because you learned about elimination yet or no?
We did, but now we.
Yeah, not so much though, because addition has more type of, you can do more with addition reactions. That's why. But normally in an elimination reaction, you start off with what this reactant looks like, and then you add an alkene right after you eliminate your certain atoms on the molecule. So it couldn't have been elimination. Can't be substitution because we're not substituting anything. Substitution reactions, we don't work with alkenes first. We work with usually an alkyl halide. So let's say we had this same molecule, no alkene though, and we had a bromine here. And then we do whatever type of reaction to get this. This is known as a substitution because you substituted bromine for OH. So it wasn't substitution. And it's definitely not Bronsted acid and base because we're not working with the acid or base and donating protons and electron lone pairs. No.
Yeah.
the answer choice was addition.
Dang.
Any questions about this question?
So Bronsted acid/base, that is a reaction, right? Because I thought it wasn't a reaction.
That is a reaction. It's like before we touched up more in addition, we worked with, let's say, sometimes you had H2O plus H2SO4, and then so your water would act as I think the base. Yeah, your water will act as a base, and H2SO4, that's sulfuric acid, so that acts as your acid. So after that little proton donating and all that stuff, you get H3O plus and HSO4. This is a base reaction, but we don't see nothing like that happening in this reaction.
Yeah, so you're saying it had one arrow to the right, one arrow to the left? That's what you're saying?
Right, because in all acid base, you could always go back and forth. Like after creating the conjugate base in acids, there's always a way to get back to H2O and H2SO4.
Okay.
Yeah, that's what those two arrows mean. All right. Any more questions about this question? Okay. So let's move on to question 10. It said, which of the following carbocation... Oh, wait. Skip the question. Which alkene reacts with HCl, so this is electrophilic addition reaction, at the fastest rate? So addition reactions, where you're working with alkenes. So this was answer choice A. Then was B. Then it was C. Then D. So HCl, it would be an addition reaction. So then you end up adding chlorine to any of these molecules, right? Now, it's about which one of these molecules will work with HCl better at a faster rate. So what do you think we have to think about when it comes to this question?
When I did this, I had no clue, but I counted if it was tertiary between the edges of the lines of the double bond.
Exactly. For addition reactions, what happens is we have to normally look out for carbocation rearrangement, right? We have to look out for that. And in this case, whenever we work with HX, like H and a halogen, in this case HCl, we will always have carbocation rearrangement. So now we're trying to look at the molecule where when you break the alkene, where's the carbocation going to be the most stable at? So let's look at A. If we were to break the carbocations, what position would the double bond, if we were to break the double bonds in A, what positions would the carbocation fall on only?
Secondary.
Right. Secondary here and secondary there. What about B? If we were to break that double bond.
But with a tertiary with a rearrangement?
Yeah, tertiary after rearrangement. So, for example, you first break the double bond. It will most likely jump to the secondary first, never the primary. And then you can do your little hydride shift and then on the tertiary, right? What about C?
Tertiary.
Right, it can also land in the tertiary position. So first secondary, then rearrangement, tertiary over here. And what about D?
Secondary.
Right, they're both going to be secondary. So we can see that automatically we can eliminate answer choices A and D because they do not give us a tertiary position. Now, we have B and C. We have both a secondary and a tertiary position for both of them. However, what's different about the alkenes?
Huh. What's
If you notice, there is a difference in the placement of the alkene, like before breakage and all that.
It's closer to
What's
the
the difference?
one.
Hmm?
It closer to the substituents.
It goes into what?
To the substituents, like the 2-methyl.
Oh, in other words, it's more substituted, right?
Mm-hmm.
yeah.
C is a more substituted alkene than B.
I choose C because I think it didn't have rearrangement.
So C, in some cases, most likely when you break the
The double
so you break the double bonds, and then it could pop onto that the tertiary position, but most likely the carbocation can still exist in a secondary position too when you pop the alkene. So that's why in certain cases, even though the double bond could be connected to a tertiary carbon, we still have to worry about rearrangement because the secondary carbocation can still form, and then you would use a hydride shift to change it. So C is also the answer because of how more substituted the alkene is. Remember, alkenes are more stable the more R groups it has attached on each side. So B, you have what's called a mono-substituted alkene because it only has one R attachment on one side, and on the other side is 2 hydrogens. So this is called mono-substituted. And then on the other side, C, is it mono? No. I think this is tri-substituted because on one side you have 2 methyls, and on the other side you have one. Either di-substituted or tri-substituted. I'm going to say tri-substituted. So that stabilizes the alkene first, and then after breakage, you stabilize your carbocation, and it'll react way faster with HCl than B.
Yeah, Mr. Kemi, when you're counting the tertiary and secondary stuff, how are you counting it for like B and C?
Oh, so
yeah.
Like, how do you know it's tertiary?
Yeah.
Oh, so remember, it depends on the amount of carbons that carbon with the carbocation is attached to. So let's say you have a carbon with a carbocation, right? Let's say you had this. This would be primary. Oh, I hate when it does that. This one that I drew here would be primary. In other words, we show primary as a 1 degree like this, because this carbon with a carbocation is only attached to one other carbon. For secondary, that's when the carbon with a carbocation is attached to 2, right? It's becoming more substituted. So this is a secondary one. Then tertiary one, that carbon is attached to 3 other carbons. So this is tertiary. And in most cases, we don't talk about it a lot, but you do have it. Quaternary, which is where the carbocation carbon is attached to 4 other carbons.
Yeah. And you're saying if it's secondary and secondary, it's just not right because...
Not that it's not right. Like, carbocations can exist in a secondary position, but we always try to form the most stable carbocation so that the addition reaction happens even quicker. The more stable you can get it to be, the more quicker the reaction will happen, because in the end you'll form a more stable molecule. So molecules where the carbocations could attack a tertiary position would be way better than just having them in a secondary position.
Okay.
Yeah, that's how it works for carbocation.
Yeah. Okay, that makes sense.
All right. Any more questions about?
No.
All right. So let's move on to question 11, which is also related to carbocation stability. So keep in mind what we just talked about. So 11. Which of the following carbocations is most stable? So let me draw these in. You have all these different types. This was answer choice A. Then you had B. Then you had C, which was this. Then you had D, which was this. And then you had E, which was this. So we have all these different types of carbocations, right? So first, let's try and identify what type they are. Looking at A, what type of carbocation is that?
Secondary.
Primary.
Primary.
Yeah, remember, it's the carbon and then however many other carbons is attached to. So this carbon is only attached to one other carbon.
Okay.
And then the rest would be hydrogens. So this is a primary. What about B?
Methyl.
Right, it's just a methyl. What about C?
This is secondary.
Is what?
Secondary.
Tertiary. So you have the carbon in the middle, right? How many other carbons is attached? Oh, wait, secondary, my bad. I didn't see that H. Secondary. Now, what about D?
Allylic, I think it was.
Yeah, it is an allylic carbocation. So that means what?
It can resonate.
Right. It resonates with this double bond here. So this double bond moves over, and then the carbocation could land in this position afterwards. And what about E?
Tertiary.
Right. You have a carbon attached to 3 more carbons here. So this is tertiary. Now, out of all these carbocation classifications here, which one do you know is the most stable?
The allylic D.
Exactly. Any form of resonance that can happen with the carbocation will always win in stability. It's like above the tertiary most stable. So like you have primary, which is least stable than secondary, which is least stable than tertiary. And if you have any chance for resonance, resonance will always win.
What did the question ask?
Oh, the question asks where is it? Which of the following carbocations is most stable?
And it's
So the
allylic.
allylic one, right? The allylic one would be the most stable.
So what would be the least stable?
Would be the one that's primary. So that would be A.
Isn't it the methyl?
Oh no, methyl.
Yeah.
Methyl would be the least because first is methyl, then it'll be primary, secondary, tertiary, and then further on, if and only if you can, resonance.
Yeah. Okay.
Now, let's go to question 12. How many intermediates and how many transition states are there during the progress of the following reaction? So this reaction was this. You had this molecule, and then you had a HBr, and in the end, you have made this. So what type of reaction took place?
An addition.
Right, addition reaction. So transition states show bond breaking and bond making. And the intermediate is normally the product after a transition state has occurred. In some cases, intermediates deal with if you form carbocations during the reaction of the molecule. And in this case, we can see that a carbocation will happen and cause rearrangement because we see where the bromine ends up here instead of the 2 carbons where the alkene was originally. So to understand this question better, it's best to try and draw out how the reaction took place in the first place. So let's do it step by step.
So
First,
the double
you
bond.
got this. Right, double bond would break. And the way that happens is the pi bond breaks and electrons grab the hydrogen.
Mhm.
And at the same time, this hydrogen bromine bond breaks and the electrons hop onto bromine, right? So that leaves with a negative charge. So after that, you have formed your first
Intermediate.
intermediate, which is the carbocation ends up in this secondary position and your hydrogen had ended up here. Now, after that, what had occurred?
The alkyl shift.
Right, an alkyl shift, because we can push that carbocation into a tertiary position because it's next to what's known as a quaternary carbon. So whenever it's next to a carbon with 3 other carbon attachments, that's an alkyl shift. So this carbon-carbon bond breaks and then form a new carbon-carbon bond with this carbon here. And then you form, what else? What do you form after that? Oh, what is this known as? Your second intermediate. Remember, intermediates show the carbocations. So you have your alkyl shift, and then you have your second intermediate showing where the carbocation lands in a tertiary position. So, wait, I'm missing the alkene. Am I? No, I'm not.
No.
All right. And then after that, what's the last thing we do?
The bromine attaches itself to the.
Right. So remember, we do have a negatively charged bromine, and now one of the electrons will
I'm in a
attack
review
the
class right now.
carbocation, and you would have formed your last and final step in the product. So it'll be this. Now,
So there's 1, 2, 3 transition state and 2 intermediate.
exactly. 3 transition states and 2 what you call it? 2 intermediates. So you have 3 transitions and 2 intermediates. Any questions on this?
No. I'm surprised I got it right. I just guessed, but.
Yeah, it's good. It's good. It's good. It's easy to miss certain transition steps. Like in some cases, which I'm pretty sure might go through some students' head, they might not even have counted the alkyl shift as a transition state, but it is. Anytime you're making and breaking bonds in any type of way, that will automatically be your transition state. So you have 3 transitions. The first step, it all counts as 1 because it all happens at the same time. Then the second step of the transition is when you did your shift. And the third was when you had made your bond with bromine and carbon. Then you have your intermediates. Your intermediate when you first break the pi bond to form your secondary carbocation. And after the alkyl shift, you have your second intermediate. Cool. Right. Any questions before I move on?
No.
All right, cool. Let's move on to question 13. So, which of the labeled points in the reaction profile indicates an intermediate? So he drew some type of chart. Let me just do that. Let's choose this color. It's a chart that looks like this. It says reaction coordinate on the bottom. That just means how the reaction goes along. And then enthalpy here. And then he had like one was here. Then boom, boom, boom. I think it looked like this, then this, then here. So You had 1, 2, 3, 4, 5, 6, and then 7. So, which of the labeled points in the reaction profile indicates an intermediate?
Intermediate. Okay.
Yeah,
3, and what's the other number? 5.
right. 3 and
Yeah.
5 are your intermediates. So what would be 2, 4, and 6?
Transition state.
Transition.
Exactly. 2, 4, and 6 are your transitions. And obviously 1 and 7 are something else. So what's 1?
Reactant.
It would be your reactant. Your reactants. And then 7 would be what?
The product.
Right. Products. Ooh, that color is bright. 7 would be your products. Top of the peak transitions, bottom of the peak intermediates, and every time you have your beginning and your very end, that's your reactant in the top front and your product in the bottom left over right over here. Cool. So it was 3 and 5. Nice. Question 14. Which of the following correctly describes the nature of the transition state of the rate determining step of the hydrohalogenation? So that's a that's a HX addition problem of propene. So you're just adding like a halogen to propene molecule. So A says that the transition state equally resembles products and reactants. Is that true? So let's say you had a C, let's say you had a methyl, an ethyl. No, let's do some other transition.
You said
Not
that
this
they're
one.
equal?
Yeah, that's what the first statement said. Huh?
I didn't put that, no.
No, it's not true. The transitions, it do show the bond making and breaking. So let's say we're doing this. We're breaking CH, right? We're gonna break CH and we're gonna make CBr. So this is how the transition state is. It'll always show 2 full bonds and 2 partial bonds. That's represented by the dotted line. So it doesn't resemble the products and the reactants equally. B says that it resembles the reactants more than the products. Is that true?
No.
No. And the last choice, it says it resembles the products more than the reactants. Is that true?
Yeah.
Yeah, that's the answer.
Okay.
Yeah, that's what I put. Isn't that usually like that? Like always?
Yeah, it is. It's always like that because the transition states is to help you understand how the bonds are making and breaking, but it's happening because it'll lead towards what you was forming. So you're breaking off CH and you're trying to, initially you're going for CBr to be made. It'll always resemble the products more than the reactants. It's just showing you how it gets to the product.
Yeah.
However, if you chose A, well, you guys didn't, but whoever chose A would get partial credit because, you know, in some cases it is easy to think that, you know, because we're showing the making and the breaking, and we know eventually it would lead to the making, but at the same time we are still breaking a bond, so it is easy to say that it can show them equally. But the right answer is it shows the products more than the reactants. All right. So now let's look at question 15. That one was a doozy. 15 was funny. So It says consider the following reaction profiles. Choose the best description of the thermodynamics of the reaction. So you have like two charts, right? The first chart, this is enthalpy and the bottom is reaction coordinate. First one you had, let me try and draw it exactly. So you had one here, then boom, boom, boom. So it was 1, 2, 3, 4, then 5. And then for the second chart, you had this. Boom, 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 boom. Oop, I wasn't there. 1, 2, 3, 4, 5. All right. So you had these two charts. Now, answer choice A said that reaction 1, which is this reaction here, and this one would be reaction 2. So it said reaction 1 is endergonic and reaction 2 is exergonic. Do you think that's correct?
No, reaction 1 is exergonic.
Right. What automatically lets us know that it's exergonic?
The product is lower than 1.
Right. The product is lower in energy than the reactant. Whenever you're going from a molecule higher in energy to a molecule lower in energy, that is an exergonic reaction. This also lets us know that there was a lot of energy released, right? So like this long line here, obviously there had to be some energy released here so that the products could be lower in energy. 2 and 4 is your transitions, 3 is your intermediate.
Yeah.
So reaction 1 was definitely exergonic. What about reaction 2? It said was what? Endergonic, right?
Yeah.
So what lets us know it was endergonic?
The product's higher than the reactant.
Right. Your reactant was lower in energy than your product. So you had formed an unstable molecule in this reaction. That's always an endergonic because remember, energy is absorbed instead of being released. So that energy absorption, like which is normally around here, lets you know that we was trying to break a strong bond at first. So energy is absorbed. Then after it's absorbed, the bond breaking happens in this transition state here. Then you form your intermediate of this unstable molecule, and then you had made a bond too, but your products still end up higher in energy because it's still not pretty stable. You formed weak bonds in the end of your reaction. So that's why it's endergonic.
Wait, Mr. Kemi, isn't it when bonds formed, the energy's lowered or something like that?
Energy is lowered when bonds form. That's why you see this little dip here between 2 and 4. And that's why it also went down after 5 too. So like the transitions up here, this was the bond making and breaking. After it was formed, like this was your first bond formation here to form your intermediate.
Yeah.
Then after 4, you have formed another bond. You have formed a bond. So it did come down lower in energy. However, the product is still higher than the reactant. So that lets us know that we have made a very unstable molecule.
Okay.
So that we can also relate that to the types of bonds we form too. We had to have formed a weak bond because the energy is still higher than the reactants. Now, let's go to question 16. So question 16 states, consider the following reaction profile. Identify the intermediates. So same little chart here. Reaction coordinates, enthalpy is here. Then you had so you have 1, 4, 2 was up here, then 3 was somewhere right here. So they say identify the intermediates. Do we have any intermediates in this reaction?
No.
No.
I was laughing on this
We
one.
don't. Right? I can only imagine how many students chose 1. I know somebody had to choose 1. They had to have looked at 3 and said, "Oh, maybe that's intermediate."
I did that.
Oh, so no.
No.
There was a question
The
on the thing in his lecture about the same chart, and I thought it was 3, but I guess he has something different.
oh no. So
The-
I'm trying to think of what D represents. Honestly, I think that would be what would 3 be? So 2 is obviously the transition. We know that's a transition for a fact. And then 3. I'm trying to think what could possibly be 3. The point of the matter is 3 is not a intermediate. So intermediates are known after like a bottom dip in
Yeah,
the
like a
energy
gap.
chart. Like
Yeah.
this will always be your intermediate.
Okay. Yeah, that makes sense.
I need to ask Ben what 3 could possibly have been. That has to have been like a what could that be? I can't even say bond forming or bond breaking. Maybe this reaction had like a catalyst added in some sort. So a catalyst is something that you can use to help like speed up a reaction. So I'm trying to think of what it could be, but
Yeah,
no,
that's
there's
fine.
no intermediate.
Okay.
All right. 17. Consider the following bond heterolysis. So RBR. So they have like RBR to R plus and BR minus, where R is an alkyl group. So you have an image below, and for these reactions, choose which reaction represents the correct carbocation. So you had this chart, same chart. First, they all met at one point, and then you had this. Then you had this. So 4, 3, 2, 1. There was a typo in this question, so you did see like 1, 3, 3, 4. Obviously, that would not be the correct answer because he missed 2. So, carbocations. The more stable kind of carbocation would be what? Higher in energy, higher or lower in energy?
More stable, lower, and then
Right, lower. So, keeping that in mind, let's identify each of these carbocations. So, 4 is the highest. Which carbocation is that one?
metal.
Right, that would be your methyl. Now, below methyl would be what?
Primary.
Yeah, 1.
Right, your primary carbocation. After primary is?
Secondary.
Right, you have your secondary. And then your final is what?
Tertiary.
Right, tertiary.
I do it backwards. Before you're doing it like that.
What, so like methyl was 1 and then tertiary was 4?
No, I put tertiary, then secondary. I started from 1.
Oh.
Yeah.
Oh, yeah. It's easy to start from 1 like that because you know the lowest in energy will always be the most stable. So it's easy to work from more stable to high. And if he really wanted to get fancy, which I think he should have added because they do exist too, quaternary, which is definitely more stable and lower in energy, would be somewhere like right there. So this would be a quaternary.
Wait, so metal has the highest energy out of all these, and then enthalpy means like energy, right? It's another word for it.
Yeah.
Okay.
So methyl is the highest because that's a carbocation. That's a carbon. Oh, carbon, and all the other attachments is just hydrogen. There's no type of carbon attachment whatsoever. So, oh my lord, a carbocation like this is very unstable. Right. Cool. Let's go to question 18. Which statement about reaction A and B is false? So let's see. Reaction A was so you had this, and then hydrogen is here. Then you had negatively charged CH1, and this is known as cyanide. And then you formed so this is reaction A. Then reaction B, kind of the same thing, but this time the cyanide had attacked a different place. So you have your carbonyl, then you have your cyanide, and it had attacked electrons push carbon here, electrons went to oxygen, and you've opened up the carbonyl, have a negatively charged oxygen, and then your cyanide is attached. So this was reaction B. So let's look at each of the following statements. It says here, A says reaction B is exothermic. Is that false?
No.
That's true.
No, it's not false. We have created a more stable molecule. So this carbon, we do have polarity in carbonyl groups. Remember that. So because of the polarity, we do have an electron deficient atom, which would be this carbon here. So this was partially positive. Oxygen is partially negative. Polarity is going this way. So this carbon is attacked with the cyanide. After it's attacked, you create a more stable bond. The carbon now has these 4 bonds. There's no polarity. Oxygen is negatively charged. Cyanide is attached. So it is a more stable molecule. So B isn't false. I mean, this isn't false. Reaction B is exothermic. Now, B says reaction A is endothermic. Is that true? Oh, snap. I didn't even see that here. Wait. Where is... I forgot to add this. There we go.
What did it ask?
Endothermic. Is that... It said that reaction A is endothermic. Is that false?
I think it is true.
Yeah, that's true. A and B were true.
It's true.
Yeah.
Exactly. Look, we ended up, after we snatched that proton off and cyanide took it away, we've created a carbon with negative charge, right? This one with a negative charge is very unstable because that negative charge is on a least electronegative atom. So it is definitely endothermic. You went from a stable molecule to an even more unstable one because of those lone pairs. So A, B, true. Now C says reaction B converts a strong base into a comparatively weaker base. Is this true?
I was choose C as my answer, so I go say no, it's not true.
So it is true. So let's think about it. You always create your conjugate bases, right? In this case, we're looking at Lewis acid base reaction, right? So you had a negatively charged carbon here. After you do all that reaction, the negative charge ended up on oxygen. So oxygen is negatively charged, but is it a strong base? Can you use these electrons on oxygen to react, like in a big amount?
Yeah. Pretty
The
sure.
problem is, you could probably, but the oxygen, remember, oxygen is more electronegative than carbon. So what does that tell us about the reactivity of these electron lone pairs on oxygen? Are they very reactive or less reactive?
The oxygen, like the lone
Mm-hmm.
pairs on it,
Mm-hmm.
are they faster or slower than the carbon lone pairs you asked?
Yeah, are they more reactive? So would the electrons on oxygen be more reactive than the one on carbon?
Yeah. Yeah.
No.
Oof.
It'll be vice versa. The reason is because of electronegativity. Remember, more electronegative atoms can always handle a negative charge better. So that means these lone pairs on oxygen right now, they're not as reactive as these lone pairs was on carbon. So the answer is C is actually true. We do form a weaker base afterwards because the electrons on oxygen, they're not very reactive since it can handle a negative charge better. So C is true. Any questions on that?
So oxygen's more electronegative, so that means its lone pairs are slower than the least electronegative.
Exactly.
Okay.
So it's
Yeah.
not a strong base because of that.
Okay.
Right?
Yeah.
So C is true. Now D says that reaction A converts a strong base into a comparatively weaker base. Is that true?
I think that's false. That's the one I
Right.
chose. Yeah, it's
This
false.
will be your false statement you're looking for. This is definitely your false statement. Because look, the base reacted with the hydrogen, right?
Yeah.
Now, after that reaction, where does your negative charge end up?
In reaction A and the bottom right.
Mm-hmm. Right. It ends up on a carbon again. So when you look at it, this base here, it is very reactive because carbon is less electronegative. So you have a negative charge on a less electronegative atom. So you've converted a strong base into a strong base.
Because it went from carbon to carbon, essentially.
Right. The basicity reactivity, if you look at it, it never changed. It's still on a carbon.
Yeah.
Versus B, we do see the actual change. It went on a more electronegative atom. So we can say that we have formed a comparatively weaker base. But in A, we didn't do that. We've converted a strong base as well.
Okay. Yeah. Yeah, that makes sense.
Yeah. All right. So let's go to question 19. Oh wait, any other questions about this problem before I move on?
No.
All right, as long as you guys get it. So let's clear this and move on to question 19. So which of the following is the correct mechanistic first step in the addition of HBr to 2-methylpropane? So we had different answer choices, right? We had this HBr. We had B. I'm sure the arrow movement in just a minute. I'm just trying to write out all of these since it all looks the same. And D. All right, now to show the arrow movement. So A showed it like this. B showed it like this. No, it showed. C showed it like this. And D showed it like this. Now, we have all these different arrow notations. In the first step of is in an addition reaction, what happens?
The will take hydrogen and at the same time that
Right.
one that got broke go to the bromine. So B.
Right. So double bond breaks, grabs the hydrogen, and then the electrons between H and whatever, let's say X, goes onto X, right? Which is the atom that can handle the negative charge better, the more electronegative atom. So the arrow movement is supposed to be from the pi bond breaking, because remember that's a base. It has electrons in there we can use. It's supposed to be from the pi bond breaking, grabbing the hydrogen, and then between HBr, those two electrons are supposed to go on to the halogen. So which of these answer choices correctly show that?
B.
B.
Yeah, B.
Exactly. It ain't A, because that's not how it works. The tail of the arrow and the head, the tail always represents where the electrons are going to move to. So the tail starts from the electrons, and the head ends up goes to where? So where do the electrons go? When I saw D, I had to bust out laughing. I was like, I hope. I swear to God, I hope. Nobody would choose that. All right. Let's move on to question 20. What is or are the major products of the following reaction? So question 20, we have, let me do that in black. We have this going on. So we have an alkene with 2 methyls, and then we're going to react it with H2O in sulfuric acid. That's going to act as the catalyst. Catalyst just means it's use this solvent to speed up the reaction to get the product more faster. So this forms what is the question. Now let me draw the answer choices out. Then we have, this was 1. Then we have this was 2. This was 3. And then lastly we had 4 of H 4. So first, before we even get to the products, let's understand how this reaction is going to work. We're working with water and H2SO4. So there are a few things we need to think about. Will there be carbocation formation with this reagent? Yes, there's definitely carbocation that's formed. So when a carbocation forms, what happens?
We want our. Oh, I forgot.
What do we have to look out for when a carbocation is formed?
Tertiary position, stuff like that.
Right. So, in other words, rearrangement. We always look out for rearrangement once we know a carbocation can form. Now, what is the stereochemistry of this reaction? If you remember.
You talking about mark and anti-mark?
So that, yes, the ratio stereochemistry, definitely. Will it
Okay,
be
so that's
Markovnikov or anti-Markovnikov?
mark. So that will
Right.
eliminate 2 and 3.
Right. It'll be Markovnikov. So 2 and 3 is definitely out of the question because we see is on the least substituted carbon. So 2 and 3 is out. And then the stereochemistry is it'll add on an anti and syn formation. So that means when we put OH on, it'll either be on a dash or on a wedge. So it attacked the front or the back of the carbon. So then 1 and 4. What do you think about these answer choices? Is either one of them correct or is both of them good?
Aren't they both correct?
Both of them are correct.
Right. 1 and 4 are both good. We said that this stereochemistry was anti and syn. Both 1 and 4 show that. First OH is on a wedge in one, and OH is on a dash in the next one. And they are Markovnikov because they're on the more substituted carbon. There was a carbocation rearrangement because you see we could break the double bond and it could have been here first. So then we use a hydride shift.
So if it was anti, wait, no, never mind.
That's all right.
What happened? No, I was thinking about something.
Mm-hmm. So if it was anti, you would only it would be trans still. Anti means trans. So let's say it was only anti, then the answer choice would be 4 because the OH is anti that methyl. We have a methyl on the wedge there. So the stereochemistry that we're going to be added on is based on the wedge attached to that methyl.
Okay, but Markovnikov means you need a tertiary position, essentially.
Oh no. So Markovnikov means that the carbocation formation will happen regardless of Markovnikov and anti. All that those two means is where exactly the OH is going to attach on the carbon. Will it be attached to the least substituted after carbocation rearrangement, or would it add to the most substituted carbon? So this carbon here would be the least, and this carbon here would be the most substituted. In some cases, with some reagents, we see that OH is indeed added on an anti-Markovnikov style, and that's only for certain reagents. That's the ones that don't have carbocation rearrangement. That's when OH is added to the least. But in this case, we have carbocation rearrangement, and because of that, OH is going to be added to the molecule in a Markovnikov style.
Okay. Yeah.
It's a lot to take in, but once you study the reagents even more, like that chart, that summary of additions chart he has at the end, study that very well because that will definitely help you with addition reactions. It helps to try and understand the mechanisms of each too. So you don't have Ben always says you don't have to remember the mechanisms, but do understand how they happen for each of the reagents, so you know that, oh, okay, it's because this happens this way, that's why there's rearrangement, or it's because this makes a ring, that's why there's no carbocation, etc., etc. All right. Oh, question 21 was fun. That was a good one. Let's do that. So, match the reagents with the correct reaction pathway. So he had a big box. I'm not going to draw the box. I need all the space I can get with this whiteboard. So we have this. After the whatever reagent we use here, we have made this. Then in pathway 2, we have made this. Oop, there's nothing there, just a metal. And then pathway 3,
What do I get if I win?
we've made this. Now, the reagents that were listed in the answer choices was, let's say 1. It was the BH3 and THF with sulfuric, no, not sulfuric acid, whatever this is, and I think this was peroxide and hydroxide. So that was 1. The second reagent is H2SO4 and water. And the third reagent available is HGOAC2H2O. So this was 1, and then 2 was BH4. I'm trying to remember what this reagent was called. I'm so sad, I don't remember. There was a name for this reagent for 3, but these are the 3 reagents available. So, which one was used accordingly in pathway 1, pathway 2, and pathway 3? So, the products made can actually help us determine what type of reagent was made. So, for example, let's look at pathway 1. Where did the OH end up after the alkene break-in?
The least substituent, so it will be
Right.
anti-mark.
So, it was anti-mark.
Mm-hmm.
It was anti-mark. So,
That
do you
our
think
first.
there was any carbocation rearrangement?
No, I don't think
No.
so.
No. There was no rearrangement. If it ended in anti-mark, no rearrangement. So this already tells us what could be the possible reagent used for 1. Now, let's look at 2. What happened? Where did OH end up?
In the more substituted side?
So it broke,
Not
yes.
really.
So let's just say secondary position. It ended in a secondary position. So do you think there was any rearrangement?
No.
No. No rearrangement. That carbocation has stayed in a secondary position after bond breakage. So it still is Markovnikov, though. It did ended up on the more substituted side of that secondary carbocation, because after it break, you can either form a primary or a secondary. It's just that there was no rearrangement that happened. So OH still did end up on a more substituted carbon. So it is Markovnikov. It's just that there was no shift. Now, what about 3? Where's the OH?
In the most substituted one, so there was
Right.
rearrangement.
So there was rearrangement, definitely. Since it was on the most, it is Markovnikov. So, rearrangement. All right. This is all the information we need to tell us what did what. So, what do you think we use in number 1 to form, in pathway 1 to form this product?
1 BH3THF.
Exactly. This is a very well-known reagent to do this sort of addition reaction.
Mhm.
Now, what about 2? It is Markovnikov, but there's just no rearrangement.
I think it's the magnesium that do that.
Which one?
I believe the magnesium 3.
Yeah, the third one.
Yes. Oh, now I remember. It's mercury something.
Oh, that's
Mercury
mercury, not
something is the
magnesium.
name of that reagent. Yeah. Hg is yeah, I think it is mercury.
Yeah.
Or yeah. So definitely 2 was 3. Reagent 3 is definitely used to do this because it's still Markovnikov, remember, because the OH ended up on the secondary carbon instead of the primary. It's just that there was no rearrangement. And lastly, the only anti-choice left for pathway 3 is the H2S, is the water and sulfuric acid. So this is a very well-known reagent to do this type of reaction in pathway 3.
Yeah. Quick question, right? Are you saying rearrangement? What do you like mean by that term? You mean like it moves like a
Right.
lot?
So what I mean is, you see how the OH ended up in the secondary position? That means that
Yeah.
the secondary carbocation did not shift to a more stable position, which is a tertiary position. So let's say it did, then it would have been a hydride shift. But because we see the OH in a secondary carbon, there was no type of shift movement whatsoever. So there was no rearrangement.
Wait, could you show what a secondary is for that one? I'm getting
Yeah,
a tiny.
secondary is let's go to the original alkene up here. Let's say we break this double bond, right?
Yeah.
You can form 2 types of carbocations here after that bond breakage. Well, 3 types if you include the shift. It can be the primary.
Yeah.
And the primary could also cause a shift to the secondary, which would be here. And then if you were to do your hydride shift from the tertiary carbon up here, you can end up with a tertiary carbocation here. So primary, secondary, tertiary.
Okay.
Yeah, so that's what
Yeah, and another
and
question.
you do see in each case that each product does show OH on all the possibilities of the carbocations, the primary, the secondary, and the tertiary. What's your question?
Yeah, the other thing I was gonna ask was when you mean mechanism, you mean like just what you wrote in the red text, the anti-mark? Cause
so when I say mechanism, is like how the reaction is carried on. So for example, I'm gonna erase all this. For the
hello, Druk.
Hg something something something. Let's say we're doing that reaction, right? Let me draw it. So we were reacting this product here. When we use the HgOAC2 and H2O, and the second was BH4, what happens is the alkene breaks, right? But the reason there was no rearrangement is because you form a 3-membered ring with the HgOAC2. This is the mechanism. You go from this to this after your first step.
Yeah.
Right?
Yeah.
You do that. Then, what happens next is you have the H2O. You have the H2O. So, oxygen has these lone pairs, 2 lone pairs. Since it is Markovnikov, it's going to be added to the most substituted side. So, it is going to attack this carbon here. One of the lone pairs attacks this, and then the membrane would break open, right? So then you have this. OH is here, And then to this carbon, we still have the HGOAC2. The second step, BHF, what that does is it just automatically takes off all of this HGOAC. So nothing too strenuous. All that happens at the end is you have your OH here, and then attached to that carbon, you'll have an H. So this is the whole mechanism to get your product. It's just how the reaction is carried out. So that includes all your Markovnikov, your rearrangement of any possibilities, etc.
Okay, and then last thing, right? Why is the OH stay? Like, isn't the H2O part of the first line with the HG, so that they both should be deleted? Or
Oh
not?
no, so water adds on. So the BHF only technically works with the HGOHC to take all this off. The water we need to add OH. So water's added, and then I think after the HGOHC breaks off, I believe it grabs the hydrogen, the extra hydrogen off of the water too to make your OH. I believe. But this is basically your normal mechanism for using this reagent. So that's what I mean.
Yeah, thank you.
You're welcome. All right. So let's move on to the next question, which was question number 22. It's another type of addition reaction too, by the way. So it said in the presence of something, a peroxide, so that's exists as ROOR. HBr addition is anti-Markovnikov. So in peroxide, HBr is anti, always, just because it's like some sort of phenomena that happens with the peroxide. So what is the product of the following? If we know it's anti-Markovnikov, we want what on the least substituted carbon? In this case, what's going to be added to the least substituted?
So bromine will go to the least substituted side?
Right. So after this reaction takes place, bromine ends up to the least substituted side. So rearrangement. Wait, did I do that? Why did I do that? Shouldn't it be here? Oh no, it'll be here. Anti-mark. So rearrangement, yes, but then hydrogen was added here after the HBr break-in, and bromine was added. What's up?
Isn't the least substituted side the other carbon? Like top right?
So we're not going to worry about the primary here because with HBr addition, we know that carbocation rearrangement will always occur. So that means we automatically withdraw the carbocation after bond breakage on the secondary position. Then you know a hydride shift could occur. But instead of the shifting occurring with the peroxide, the bromine is just going to add on the least substituted carbon here. So it's going to add here, and then hydrogen is here. Hydrogen is here, I think, as here. Oh no, I'll look at the answer key when Ben posts it. But he physically looked at this exam when I did it, so when I chose C, I don't think he said that was the wrong answer. But if it is, then it might be D, where bromine was added here. Might. I'll check the answer key for that when he posts it.
Well, so right now I have 2 questions run.
Have the what?
I have 2 questions run.
Oh, good. So far?
Yeah.
Oh, that's all. Well, I don't mean good you have it wrong, but I mean good that is only 2 so far, because that's good. All right. Now let's look at 23. Which of the following species is the intermediate in bromination of propene? So that reaction is like this. You got this, and then bromination, it's the Br2. Yeah, Br2. And normally this reagent is done in let's say H2SO4. Not H2SO4, water. I believe he's trying to say water. So bromination. So what is the intermediate? You have
So
answer
we're going for
choices.
carbocation on this one.
No, we don't form it.
So we can eliminate the one that have a carbocation and that negative charge over there.
So let's see. All the answer choices showed this. Let me just try and draw them in quickly. So this was A, this was B, this was C, which was this. Oh, I hate when that happens. And then the last choice was BR with a negative charge and this. So which one do you say we can eliminate?
We can eliminate A, C,
Mm-hmm.
D,
Yes.
because having the
And
wrong
C.
charge.
And which one?
Well, D because have the wrong charge.
Right, negative charge. So the only answer choice left is B, which is correct. For the bromination, the intermediate is indeed a 3-membered ring with the bromine before the other bromine comes and attacks.
Yeah.
So what happens as a result is you add both bromines in I believe in an anti-fashion. Yeah, you'll add it in an anti. So it'll be a trans molecule. So the product will actually be this. All right, good. You got this one too, Elijah? Let's move on to question 24. Which of the following pairs do not show an acid and its conjugate base? So we have H2, HNO3 and NO3 minus. We have H2SO4 and HSO4 minus. CH2SO4 and SO4 minus. And D was HSO4 minus and SO4 minus. So,
Okay,
for
C. Let's go to is C.
right, C. So remember, in acid-base reactions, you're donating 1 proton at a time. So the conjugate base would be after that only 1 proton was donated. The only one that don't show that is C, because it's saying that both hydrogens was donated at once, which is never the case in acid and base. Gotta remember that. All right, next one. The next one was cool. So arrange the following alcohols in order of decreasing pKa. So in other words, what does that mean? If you have a lower pKa, you're more what?
More acidic.
Right, more acidic. So we're going in order from basic, 2 more acidic. So let's look at the choices. I'm gonna draw them down here. OH, 1. OH. This one has an alkene. This was 2. This was 3. And then this one had an alkyne, and this was 4. So,
Okay. So 3 was resonance stable, so it's more acidic.
which one?
3 is resonance stable, so it's more acidic.
Right. 3 was more acidic because of resonance. Remember, a more acidic molecule, will always create the more stable conjugate base. So, after that proton is gone, you have the negative charge, and then that can definitely conjugate with the double bond that's there. So 3 is more acidic. Now, which one do we know is more basic?
1.
Right, 1. It only has its negative charge to rely on, versus 2, 3, and 4, it has other more effective properties. So then what's after 1?
2. Wait.
Yeah, you're
Yeah,
right.
2.
2. Now, 2 and 3 is based off the inductive effect. So remember, that's when you have a more electron withdrawing substance on the molecule that can pull electron energy towards itself. So you have an alkene, and then you have the alkyne. So it's about which one works stronger in the inductive effect. So 2 is definitely after 1. And then between 2 and 3 is 4. Alkyne would pull more electron energy away than the alkene. So this is the correct order in order of decreasing pKa. Any questions?
Nah.
No.
All right, cool. I'm glad this question was good. All right. So now let's look at the next question, which is question 26. What are the most likely product of the following Bronsted acid base reaction? So we have this reacted with H2NCH3 and electron pair. So whenever you do acid-base reactions, first you have to always identify what's going to act as your acid, what's going to act as your base. So we have carboxylic acid here, and we have amine? I believe amine. So what's going to act as your acid?
Carboxylic acid.
I mean, it's right in the name, right? So molecule 1 is going to act as your acid, and molecule 2 is going to act as your base. So how do we show the curly arrow notation for this acid-base reaction? What's going to happen?
The 2 lone pair on the nitrogen will go for the hydrogen.
Exactly. It snatches the hydrogen. Now, what happens between the oxygen-hydrogen bond here after donation?
That bond between oxygen and hydrogen will go to the oxygen.
Right. So the 2 electrons in between these bonds, it goes straight to oxygen. So your 2 products that you form in the end after all this is, in your carboxylic acid, this oxygen down here that donated, it would have a negative charge because of the electrons that was pushed onto it. And then what happens with your base? What would the product look like?
NH3 plus.
Right. H3N plus, and it's still attached to your R group. So the answer choices would be if you get this and this. So in version B, it was 2 and 4 because it showed both these products that was formed. Cool. We're like almost halfway through the exam. So now let's look at question 27. It said the conjugate base of compound X is strong enough to remove a proton from which compound so that the equilibrium favors the product. So let's do this. X was this. So then the conjugate base of this same product X would be this. The oxygen now has a negative charge. So this is the conjugate base. Now we're trying to see if we can deprotonate this. So 1, 2, which is CH2NH2, and 3, which is CH2CH3. So 1 is what? What is this group on this hexane?
Carboxylic acid.
Right. Carboxylic acid. What about 2?
Oh.
What's the functional group there?
Amine.
Yeah, so
Right. Amine. And then 3 is just an R group, right? It's an alkyl group.
Mhm.
This is your alkyl group. So what would help you with this answer choice is looking at the little pKa graph that he gave to you on like the back of this exam so that you could work on this answer. So depending on what the pKa is for your conjugate base, what does it have to be in order to be able to deprotonate any one of these molecules? Would it
Lower
have to be
than
higher? Huh?
it has to be lower than the one that they give you. I think.
Has to be lower. Where is the damn chart? I'm trying to let him grab it. Oh, there we go. So let's see. I believe it has to be close to or high. No, because it's a base. So the base is trying to deprotonate something, so it has to be. I believe it had to be bigger than 10, but it has to be close to the pKa of one of these molecules in order to deprotonate it as well. So first, you know this is an alcohol that you're working with, so you find the conjugate base of it and write its pK, which is right here. Its pK would be 17. Now, let's look for the pK of the other molecules. Oh, I said RKa. For the carboxylic acid, it took a little minute to find it too.
That's 4 on the sheet near the bottom.
Yeah. So the pK is 4.
Yep.
Now, for the amine,
It's about 35.
So that little squiggle means about, not negative. Negative is a straight line.
Yeah.
So about 35 for the amine. And then for the alkyl group, like an alkane, it says about 50. So which one of these molecules here could the pKa of this alcohol deprotonate? 1, 2, or 3? It has to be bigger than the pK of what you're trying to deprotonate in order to deprotonate it.
When you mean bigger, you mean a higher number, so it'd be 35 and 50?
Or no, what I mean is
the
stronger molecule that you're going to use to deprotonate, right?
Yep.
that pK of that molecule has to be bigger than the other molecule that you're trying to deprotonate. So we have the alcohol here. Its pK is 17. Now,
Yeah.
17 has to be bigger than one of the pKs of these molecules in order to deprotonate.
So it'd be
So
bigger
which
than
one can it deprotonate? Right. So which one of these molecules could this conjugate base of alcohol deprotonate?
Just
Be
one. Okay.
Right, just one. It can't
Okay.
deprotonate the amine because amine is too big. The pK is too big. It won't work. And then it definitely can't deprotonate an alkane because it's about 50, which is way bigger than an amine. So it can only deprotonate a carboxylic acid because its pK is lower. Which makes sense, right? In order to deprotonate an acid's pKa needs to be very low and almost negative. So this is an actual acid-base reaction that would work. You can't react in acid-base reactions with a pK of both big positive numbers. It's not going to work. All right. It's 4:02, so this was question, what, 23, 20 something? Oh, it's 27. So we was almost done. We had like, I think 5 or 6 more questions, but I can always touch the last couple in my next office hour.
Yeah. Miss Akemi, how do you think we should study for the final again? You said in your recitation you just go over the past exams?
Yeah, so I would definitely go over the past practice exams that you was looking at this whole time for like each of these exams.
Yeah.
I would study those again because his finals and exams so far you've seen has always been related to the practices. So study the practices a lot. And also take in mind the possibilities of what he can change in a question or what other type of question he can ask, like the opposite of what he's asking. Also take those into mind.
And just to make sure, is there the packet you have? It's a physical copy, right? It's not possible that you could
Yeah,
send it.
it's the physical. No, I wish, but it's not in PDF form yet.
Oh, I see. Yeah, because it's gonna be
Yeah,
a quick time by the time we get the test back.
yeah, I know.
Yeah. All right. Thank you, Mr. Kemi.
You're welcome.
Yeah,
If
thank
you
you.
guys have any questions, just feel free to email.
All right.
Okay.
Thank you. Have a good
All right,
weekend.
bye guys. You too.
All right. Take care. Fuck! I'm so fucked.